What on earth is this problem? X plus 1 squared is expanded. This is easy, but the other is... Oh, Metan, why did you give me a problem like this?
That's not it. I'm also trapped. I haven't been told the answer to this problem.
What, really?
Let's work together to solve this problem.
Well, I guess I have no choice then. So about this problem, just like expanding x plus 1 squared, it's asking us to expand x plus 1 to the pi. How should we do this?
This is a tough one. Let's move forward step by step. Pi is about 3.14, so it's between 3 and 4.
There must be something hidden around there.
The result of expanding x plus 1 squared has already been given. Next, let's try expanding x plus 1 cubed. And you get this.
I know this equality too.
Additionally, I'll write down the result of expanding x plus 1 to the fourth here.
Oh, so that's what it looks like.
Now the problem we're dealing with, x plus 1 to the pi, can be considered to lie between x plus 1 cubed and x plus 1 to the fourth.
Well, that's true, but I have a bad feeling about this. Can we really expand this?
What do you mean?
For example, let's think about expanding x plus 1 cubed. Normally you just multiply x plus 1 by itself 3 times. I'll skip the steps in the middle, but if you expand it, you'll indeed get this result. You could reuse the result of x plus 1 squared for this part, but either way, this is generally how it goes.
Yeah, that's true.
But what does x plus 1 to the pi even mean? X plus 1 is lined up pi times, but pi isn't a natural number, so you can't line up x plus 1 pi times.
I see, that's what you mean. Indeed, pi as an exponent doesn't mean multiplying the same expression pi times. Here the exponent is extended from natural numbers to real numbers, so this expression can't be expanded easily. We'll need a different approach.
What should we do?
Zundamon, do you remember the binomial theorem?
The binomial theorem? Oh, now that you mention it. If n is a natural number, the expansion of x plus y to the n is expressed as a sum like this.
You remembered it well. So what is this coefficient here?
This is called a binomial coefficient, and it represents the number of ways to choose k items from n. Binomial coefficients are also written like this.
That's right. Now do you know why the binomial coefficient appears here?
Isn't it because it's the binomial theorem, so we get the binomial coefficient?
Well, yeah, but this is an important part, so think back a little. To put it simply, let's say we have the expression x plus y multiplied 5 times. When you expand this, what would be the coefficient of x squared y cubed?
If you imagine expanding this expression, for example, by choosing terms like this, you get x squared y cubed, but there are many other ways x squared y cubed can appear. I see. So here you're choosing 3 from the 5 y's, and the number of ways to choose 3 from 5 gives you the number of x squared y cubed terms.
Exactly. So now you understand the meaning of the binomial coefficient in the binomial theorem, right? Next, the question is how to calculate the exact value of this number. If you calculate the number of ways to choose 3 from 5, the first choice is from 5 items. For the second, it's from the remaining 4 items. And the third is from 3 items. However, what we need to be careful of here is, since we're calculating the number of combinations of 3 out of 5, the order in which the 3 are chosen doesn't matter. To eliminate the duplicates caused by the order, first, you choose 1 out of the 3, then 1 from the remaining 2, and finally 1 from the last. This way you need to eliminate the duplicates caused by the order. The denominator can be expressed using factorials like this.
Oh, I remember that.
To generalize, the number of ways to choose k from n is given by this formula. And by the way, the number of ways to choose 0 from n is defined to be 1. That's the review of the binomial theorem.
I'm starting to remember it now.
Next, since x and y are arbitrary in this theorem, let's swap x and y. Then we get an equality like this.
I see now. I just figured out the answer to today's problem.
What? What did you say? Hurry up and tell me.
Haha, no need to rush. If you consider the case when y equals 1, the left-hand side looks like this, and on the right-hand side, y disappears.
This is known as the one-variable version of the binomial theorem. By the way, you can also recover the original binomial theorem from the one-variable version.
Oh, really? Well, let's continue. Now, pay attention to the left-hand side for a moment. In this expression, x and 1 are swapped, but it's in the same form as the expression in the problem. So if we forcibly substitute pi for n here, we get an equality like this. The left-hand side is the expression from the problem, and the right-hand side is its extended form.
That's certainly an interesting way of thinking. But if k moves from 0 to chi, are chi plus 1 terms added? What does that mean?
Well,
And also, what does it mean to choose k items from chi? When you think about it, this expression doesn't make much sense.
we've got a problem. Then what should we do?
There's no choice. Let's access it.
Access.
Merit Snowmodens.
Whoa, what just happened?
It seems like we've successfully accessed a hint. This is the number of ways to choose n plus 1 items from n. I see, that's interesting.
Please explain properly.
The number of ways to choose k items from n can be calculated using this formula. Normally k can only take values up to n at most, but what happens if you exceed that limit? The number of ways to choose n plus 1 items from n is, if you follow the formula, it turns out like this. Then 0 appears in the numerator, so the result is 0. This result matches the intuition that you can't choose n plus 1 items from just n.
Is that so?
Let's look at an example. According to the formula, the number of ways to choose 3 items from 3 is 1. Now if you increase the number of items to choose, and try to choose 4 items from 3, 0 appears in the numerator, so the result is 0. If you try to choose 5 items from 3, the numerator goes below 0, and negative 1 appears. Once again, the result is 0. What this means is, in the one-variable version of the binomial theorem that Zundamon proved, instead of having k range from 0 to n, you can let k range from 0 to infinity.
What does that mean? But it's true. Since the binomial coefficient becomes 0 when k exceeds n, in the end it's the same as just adding up to the nth term. So it's effectively a finite sum.
Exactly right.
Which means the only place where n is left in this formula is right here. Can we extend n from natural numbers to real numbers? If we replace the natural number n in the binomial coefficient with a real number, alpha, we get an equality like this. Here there are a lot of alphas in the numerator, but the product can be calculated, even though alpha is a real number. So this means we've successfully extended the binomial coefficient. And as usual, when k is 0, let's continue to define the value of the binomial coefficient as 1.
Brilliant, Zundamon. We've moved away from its meaning as a combination, and successfully extended the binomial coefficient. From here on, the extended binomial coefficient will still just be called the binomial coefficient, so take note.
I wonder who you're saying that to.
Now, if we forcibly extend the one-variable version of the binomial theorem, it turns into something like this. Here, the natural number n has been replaced with the real number alpha. However, this is just an intuitive derivation, and can't be considered a rigorous proof. But in fact, this formula is known as the binomial series, which is one of the results of using the powerful tool in analysis known as the Maclaurin expansion. It's also known to converge when the absolute value of x is less than 1. However, explaining the Maclaurin expansion would take too long, so we'll skip that for now.
So that's how it is? Then maybe we should have just done the Maclaurin expansion from the start.
That's one way to think about it. But the generalized view of the binomial theorem gives an intuitive understanding, and the Maclaurin expansion justifies that intuition.
True. It would be a bit confusing if someone just told me to use the Maclaurin expansion.
By the way, you can extend both x and alpha from real numbers to complex numbers too. Of course, if alpha is a natural number, then for the reasons we discussed earlier, the infinite sum essentially becomes a finite sum, which matches the original one-variable binomial theorem. Finally, if you substitute pi for alpha, you'll get the answer to the problem.
We finally reached the answer. Still, I can't believe the expanded result is an infinite sum, not a finite one. What a tricky problem.
Well, that's true. Let's try a more manageable example for calculating the coefficients. How about expanding the square root of 1 plus x? Since the square root can be rewritten as the 1/2 power, using the binomial series with alpha equals 1/2, it takes this form. I'll skip some steps, but when you calculate the coefficients, they turn out like this.
I didn't know you could expand a square root like this.
Lastly, let me introduce the fact that the binomial series is a generalization of a famous formula.
How do you know all this?
If we take alpha equals -1 and substitute negative x for x in the binomial series formula, first, the left-hand side becomes like this. Keep in mind that Raising a number to the power of -1 results in its reciprocal. Next, as for the right-hand side, let's just replace alpha and x, and it becomes like this. I'll skip the steps again, but the answer becomes very simple.
Wait, it's the geometric series formula.
Looks like you figured it out. When you line up the results like this, you can clearly see that the binomial series and geometric series are indeed similar. To go further, the binomial series is not just a generalization of the one-variable binomial theorem, but can also be considered a generalization of the geometric series.
Something unexpected came up at the end. Wow, I didn't realize the binomial theorem was so deep. I used to feel a bit unsure about it because combination problems seemed difficult, but I might start to like the binomial theorem now.
Well then, take care everyone.
See you again.